Hello to our friends joining us via recording. Today we are going to be talking about lesson number 4, which is all about how we get some things across the membrane that can't pass straight through the membrane. So to help us prepare for talking about moving these kinds of things through the membrane, we did some group work to remind ourselves about the different kinds of chemical bonds that we have inside molecules. So here's a quick reminder for us. When we talk about the things in your body, inside your cells, that help your cell to work, we call them molecules. It's when we have lots of things that come together and are connected. So the big one when we talk about our cells, we have kind of like the big 3 or 4 here. I'll type it for you. Obviously one of the biggest ones that we have in our cells are carbon. We use a whole lot of oxygen. We do a whole lot of nitrogen, especially when we're talking about proteins. Next unit, we're going to talk a lot about proteins. So lots of nitrogen there. And then our other big one is hydrogen. So if you want to take these weird concepts of these kinds of bonds and kind of put them into a real life example, when I start talking about things sharing electrons, or when I start talking about things having dipoles, consider it being carbon and oxygen that are sharing electrons, or consider it being nitrogen and hydrogen that we're talking about dipoles. So all of this vague chemistry stuff we're talking about, remember that our goal is to build the kind of stuff that your cell needs to survive. One of those things your cell needs to survive is what I like to call the energy money. What's the energy money in your cell? What's that thing that the mitochondria makes for us?
ATP.
Yeah, exactly. ATP. That's one of the big molecules that we make using some of these things here. So when we talk about chemical bonds, we're building things like ATP. Absolutely. So let's go through and start talking about our statements. I've given you 3 kinds of bonds up here. We could have also included ionic bonds in this list. I've just honestly forgot to put it in there. So we can see if there are any that also include ionic bonds. My first statement up here talks about sharing electrons. When we talk about sharing electrons, this keyword sharing right here, this is really important. There's a whole group of bonds that I called sharing bonds. Who are sharing bonds? Yeah, exactly. Several of us chiming in. When we talk about sharing electrons, we are talking about covalent bonds. Covalent bonds. Those are always my sharing bonds. Now, I know I chatted with at least one group. This statement over here was purposefully tricky. I'm curious to see in the chat some emojis. How did we feel about this statement right here? Yeah, Kira says she thought it seems fake. Kaylin said she knew it. Yep, some of my friends from the group that I popped into. Yeah, so this statement is actually wrong, right? When we're thinking about this statement is completely wrong. I know, I'm so sneaky, right? Exactly like Kira said, we never use protons to build a bond. We are never sharing protons. This is like an underline, highlight, star, important idea. The only thing we ever share when we're building a bond, it's only ever electrons. So I put this sneaky statement on here on purpose to remind us we're never ever sharing protons. Protons are always stuck in the nucleus. They're never going anywhere. We don't share them. Electrons are what we share to make bonds. So when we look at this statement here that talks about sharing protons, that's a no-go. This is nobody. Nobody is forming by sharing protons. We just don't do that. That just doesn't happen. So no bonds form with protons. All of my sharing bonds, when we talk about sharing, that's electrons that we're sharing. We're never sharing protons. By the way, when we talk about electrons, one thing we can do with them is we can share them. The other thing we can do with them is we can steal them, or if we're talking more nicely, we can transfer them. What's the name of the kind of bonds where we transfer electrons from one atom to another? Exactly. Yeah, that's my ionic bonds. So when we're talking about stealing, or when we're talking about transferring, that's the job of ionic bonds. So if you ever see this terminology, stealing or transferring, that's what we do in an ionic bond. That means somebody becomes positive and somebody becomes negative. But again, it still always comes back to electrons. It is always electrons that we're either sharing or we're stealing. Sometimes when we make a bond, we make a dipole. Now, before we talk about the specific kind of bonds that make dipoles, can you remind me in the chat, what are dipoles? We talk about dipoles. We got to know what those are. This is an underline highlight term for us here. Yeah, so when you see dipole, we should be thinking charge, absolutely, and we should be thinking partial charge. So partial positive or partial negative. I say this partial positive or this partial negative because these are things that aren't always positive and they're not always negative. If we were always positive or always negative, we would be an ion. Ions are things that are always positive or always negative. If I look positive some of the time, or if I look negative some of the time, that's considered a dipole. When I talk about forming dipoles, this happens because sometimes my electrons spend a little bit extra time around one of the atoms in my molecule. So somebody's hogging the electrons and somebody's not seeing them as much. Which kind of bond did we talk about where somebody hogs those electrons and somebody else doesn't see them as often? Yeah, several of us are chiming in for me. The full name of this kind of bond is a polar covalent bond. A polar covalent bond. Remember, we already said covalent means sharing. So this is the kind of bond where we're sharing. Polar means we are not equally sharing, right? That's what this polar word means. We don't share equally. If we don't share our electrons equally, like this bond name says, we will always make a dipole. So here's a note for us to write down, again for ourselves, something we must know. Anytime I have a polar covalent bond, I will always have dipoles. Anytime I have a polar covalent bond, I will always have dipoles. Because if we're not sharing equally, we will always have places that look partially positive and partially negative. So anytime you hear about a dipole, you should be thinking polar covalent bond. And anytime you hear about polar covalent bond, you should be thinking dipoles. So these words go hand in hand. If we don't share equally, we're going to look partially positive, we're going to look partially negative. Hey, if I look partially positive and partially negative, if I have dipoles, would I play nice with water? Would I like to be around water if I have a dipole? What do we think? Yeah, if I have a dipole, if I've got areas where I'm partially positive or partially negative, I like water because water also has areas that are partially positive and partially negative. So if I am a polar covalent bond, and I'm going to put in parentheses here that I have dipoles, if I'm a polar covalent bond with dipoles, I'm going to play nice with water, meaning I like to be next to water. Water's dipoles look really attractive to me. I like that. That's good. Hey, there's one other kind of bond from our list up there that would also like to be around water. It actually forms between water molecules. Yeah, so the one from our list that we would include would be hydrogen bonds. When the positive hydrogen is attracted to the negative oxygen in water. But Elapina, you're totally right too. The other one that didn't make my list up there that does also play nice with water are ionic bonds. Ionic bonds. Now, the thing with ionic bonds is when I put them with water, what happens? If we put something with an ionic bond in water, yeah, Kira and Fanshin are totally right. Ionic bonds are the kind of bonds that you put them in water, they're going to fall apart completely. Because remember, the only thing that keeps ionic bonds together is you're negative and I'm positive. So let's hook up. Let's be attracted to each other. If you put in something else with a positive and a negative, like water, this kind of bond completely falls apart. So ionic bonds, they play nice with water. They play too nice with water. Like they completely fall apart in water. But they love to be by water. That's totally cool. Things that have a polar covalent bond in them, they like to surround themselves by water. But remember, because they are covalent, because they share electrons with their other atom, they're not going to fall apart. They'll stay together even when they're surrounded by water. Ionic bonds don't even stay together. They just fall apart. Hey, let's go over to our similar statement on the other side here. We talked about all the ones that do play nice with water. Who does not play nice with water? Which kind of bond does not play nice with water? Yeah, exactly. My other kind of bond that we didn't talk about before, non-polar covalent bonds. Non-polar covalent. These ones do not play nice with water because remember, this word non-polar, that's kind of the opposite of water. We had a word that we'll see on the other page. Yeah, Audrey already beat me to it here in the chat. Non-polar means the same thing as hydrophobic. Hydrophobic. So a non-polar covalent bond is hydrophobic. It does not play nice with water. So non-polar covalent bonds, they don't play nice with water because, let's talk about their name, we are a sharing bond. Covalent means sharing. What does non-polar mean about how we share? What's going on with my sharing in non-polar covalent? Yeah, exactly. Equal sharing. Equal sharing, no dipoles, absolutely. So the kind of bond that doesn't play nice with water, that's non-polar covalent bonds. We share our electrons equally. We have no charges. We don't want anything to do with water. We don't need that kind of negativity or positivity in our lives. We are equal sharing. Hey, if we're sharing equally, does that mean we have similar or different electronegativities? If I share equally, similar or different? Yeah, several of us are chiming in. When we talk about equal sharing bonds, when we talk about non-polar covalent bonds, these are going to be molecules that have a very similar electronegativity. Very similar. Remember that this word electronegativity is how badly I want to have the electrons. If we both want the electrons the same amount, if we're both tugging on them the same, we're going to share those electrons equally. Non-polar covalent. We both want them the same. We have the same electronegativity. We're going to pull on them equally. Now, if we put together things that have somewhat different electronegativities, somebody wants them more than somebody else. That's why we end up with these dipoles if our electronegativities aren't very well matched. If our electronegativities are completely different, so somebody really wants it and somebody really doesn't want it, that's how we get ionic bonds. So remember that we form ionic bonds when we're completely mismatched for electronegativity. We form non-polar covalent bonds when our electronegativities are very close. And polar covalent if they're kind of the same, somewhere in the middle. One last statement up here. This statement talks specifically about those dipoles. When we are looking at two molecules with dipoles and they get attracted to each other, Fanchen is correct. Yeah, that would be the basis for how we form a hydrogen bond. How we form a hydrogen bond is when my dipoles get attracted to each other. So, last kind of bond, how do we form those hydrogen bonds? Right here. When we're not sharing equally, if one of those things that isn't getting shared equally with is hydrogen, it just might form a hydrogen bond. How do we feel about our chemical bonds? Thumbs up, thumbs down, mind blown? What do we think? Audrey says not a fan. Hey, I feel you. Chemistry is not my favorite either. I told you that, right? That's what my 4-year-old says when we try to get her to try new food. She says, that's not my favorite. It's like, okay, child, but we still got to try it. It's not my favorite. All right. Let's take these ideas of chemical bonds and let's think about them, continue to think about them as we talk more about the plasma membrane. When we talk about the plasma membrane, remember from class last week that the plasma membrane is something called the phospholipid bilayer. The phospholipid bilayer, meaning I've got two layers of phospholipids that build it. We've got our outer layer and our inner layer of phospholipids. Let's start by talking about the two parts that make up a phospholipid. So when I'm talking about the parts here in the middle, what part of a phospholipid do I call that? They're in the middle of my membrane. Yeah, several of us chiming in. The part that's in the middle of the membrane, those are called the tails. So the parts that I find on the outside of the membrane then, either outside or inside, the two surfaces, those are the parts that we call the heads. So the heads form the outside of our membranes. The tails form the middle of our membranes. Yeah, so Kaylin is helping us out as we start talking about the chemistry of the membrane. These tails here in the middle are hydrophobic. They're hydrophobic. And help me out in the chat. What does that word hydrophobic mean again? If you're hydrophobic, what does that mean about you? Yeah, exactly. Water fearing, right? Water fearing. We are afraid of the water. Perfect. Hydrophobic. When we talk about those heads, the heads aren't hydrophobic. What's the word I use for what the heads are? Yeah, like that, Elapina. Water haters. That's awesome for those tails. Yeah, so the word I use to describe my tail, or excuse me, my heads, the other part of the membrane, they are hydrophilic. Hydrophilic, which means how do they feel about water? If you're hydrophilic, yeah, water loving, right? Hydrophilic, water loving is literally what it means. So we've got these two parts of the membrane. We've got the tails in the middle that are hydrophobic. They're afraid of water. Or the tail, did I say that right? I don't even know. The tails in the middle, hydrophobic, water fearing. The heads that I find lining the inner surface or the outer surface of the membrane, these parts are hydrophilic, which means they love water. Now, we kind of said this on our previous slide, but let's remind ourselves, hydrophilic, when I use this word, hydrophilic, does that word mean the same thing as polar or non-polar? Hydrophilic, does that mean polar or non-polar? Yeah, exactly. Hydrophilic means polar. It's the same thing. If you are polar, you like water. You're hydrophilic. If you're polar, you have dipoles, partial charges. So the heads are polar. The tails then, they're not polar, right? They're hydrophobic. What's my word for those tails? My tails would be, yeah, totally right there. My tails are non-polar, non-polar. And remember, non-polar meant we don't like water. We're hydrophobic. I love it. I saw a couple fun things to help us out with this polar thing. Polar, like polar bears, they like the water. That's totally true. And yeah, Laura's saying her 4-year-old says that she's water loving. Hey, legit, I was totally going to say that my daughter is water loving too, and she's also 4. So your daughter's in good company. Hydrophilic things, polar bears, or 4-year-olds that love to play in the water. So that's perfect. Last thing for us to label on our picture here is places where we have water. When we talk about the places where we have water, these places are going to be, are they going to be next to the things that are hydrophilic or next to the places that are hydrophobic? Are they going to be by the hydrophilic parts or the hydrophobic parts? Yeah, exactly. Fanchin's mentioning near the heads. So I'm gonna do some coloring here. They're gonna be near the heads, or like Kira said, the parts that we said were hydrophilic. So we're gonna have water all around on the outside of our cell. We're gonna have water all around on the inside of the cell. So when we talk about where we find water, the quick reminder for us is it's gonna be the places that are hydrophilic. It's going to be the places that like water. If you don't like water, like the middle of this membrane here, we're not going to find water there. Like your goal in life is to make sure there's no water. So water on the outside. Hey, let's do some terminology review here. The water on the outside of the cell out here, let's pretend this cell is in a tissue. What's the name of the water or the fluid that's found outside of a cell but inside a tissue? Yeah, so it is extracellular. It's outside of the cell. It's an extracellular fluid. And a couple of us have mentioned correctly that that fluid is called interstitial fluid. Interstitial fluid. I apologize. That was a mean thing to make you type. Interstitial fluid. So if this cell was inside a tissue, it's got interstitial fluid on the outside. I've only got one word or one name for the fluid that's inside a cell. What's that one name for intracellular fluid? The one intracellular fluid. Yeah, absolutely. Cytosol. Cytosol. So I've got cytosol next to the heads of the membrane, and I've got my extracellular fluids next to the heads of the membrane. There is not fluid inside here, because I've got those lipid tails, and they're going to make sure that there's not fluid in there. So our goal for today is to figure out, how do I get things across the membrane that normally would be in the fluid on either side? Remind me, when I'm talking about the membrane, is it the heads or is it the tails that are more important for deciding what can get in and out of a cell? Who gets to decide, the heads or the tails? Yeah, exactly. The part of the membrane that gets to decide if we get in or out are the tails, this middle part of the membrane. I was chatting with someone in office hours. Think about these tails kind of like legs. So if you've got something that's coming in, trying to come in through the membrane, and these legs see it and they say, wait a minute, you don't match me. I'm going to kick you back out, literally, going to kick you out. Or if there's something here on the inside that's trying to get across the membrane, and it sneaks inside this area here, and the legs say, hey, you don't match me, I'm kicking you back in. You can't get across here. So think about these tails. The guided lesson talks about them like a bouncer. Think about them like a gatekeeper, or when you're looking at them, like I said, they kind of look like legs. So if we've got legs there that are kicking stuff in or out of the cell, into the cell or out of the cell, that might be one other way to think about it. So whatever helps you to remember, right? Legs, bouncers, or just lipid tails. You're good. All right. So I guess one last thing. We determined that the tails tell us what can and can't get across the membrane. Can you remind me in the chat, what are the words that we use to describe things that the tails will let across? What are some of the words for the things that can get across the membrane? You can get across if you're, let's make our list here. Okay, yep, so my first thing on our list, if you're hydrophobic. If you're afraid of water, you can totally get across the membrane. That's absolutely true. If you're hydrophobic, that also means you're nonpolar. Nonpolar things can get across the membrane. And Kira mentioned for us another word that we might see. That word is lipid soluble. Absolutely. Here is a wink, wink, nudge, nudge from Dr. Ollis. I promise you on the exam, you are going to see a question that asks you about which of these things could diffuse straight across the membrane. And I'm going to give you like absurd things you've never heard of before, you've never seen before. I'm going to give you chemicals, I'm going to give you elements, I'm going to give you whatever, random stuff. When you're reading that question, all you care about to help you figure out if something can or can't get across the membrane, you're looking for these words here. If I tell you that you've got a chemical that's hydrophobic, sweet. I don't care what that chemical is. I know that it's hydrophobic. I know that it can get across the membrane. Or if I tell you that a chemical is nonpolar, you don't care what that chemical is. You know it can get across the membrane because it's nonpolar. Same thing with lipid soluble. If I tell you that something's lipid soluble, that can get across the membrane. So wink, wink, nudge, nudge. I promise you're going to get a question on the exam that asks you whether or not things can get across the membrane. All you care about are these words. We're looking for these things. Is it hydrophobic? Is it nonpolar? Is it lipid soluble? Fanshin did mention the other thing that is important for us too. Is it small? If I tell you that something's really big, you know that it's not going to get across the membrane. So look for these keywords here when you're working on that question. Look for those keywords because these are the things that tell you, yeah, that could sneak across the membrane. Doesn't matter what it is. If it fits this bill, it can sneak across the membrane. So make sure we're familiar with those things. Hey, let's make a list while we're at it of the words for you can't get across. If, what are my words for that? You can't get across that membrane if, yeah, if you're water soluble, absolutely. So if you like to float around in water, no dice. If you are polar, so if you don't share things equally, absolutely. If you are large. And our one other one that we had way at the beginning, if you're hydrophilic. If you're hydrophilic. If I tell you what you're looking at is any of these things, doesn't matter who you are, if you're hydrophilic, not going to let you through. Oh, I guess there's one other thing that your lesson mentions. Does anyone remember the one other thing that's on this list from the lesson? Yeah, if you are an ion is the one last thing. So if you have a charge, so if you're an ion, you can't get across the membrane. If you have a charge all the time, so you're sodium, for example, if you're hydrophilic, so you like to be around water, if you're large, all of these things, you can't get across the membrane. At least, here's my qualifier statement, at least you can't get across the membrane straight through. Without help, these kinds of things can't get across the membrane. They're not going to diffuse straight through. But when we talk about how neurons send messages to each other, neurons love to use ions, letting ions in, spitting ions out. Neurons are all about that ion life. So we have to talk about today, how do I get those ions across the membrane? If they can't go straight through, I've got to have a different way to make it happen. And the different way that I make it happen is by using proteins. Big idea for us to think about as we're talking about our lesson today. If I can't go straight through the membrane, I'm going to use a special tunnel, a protein tunnel, to get me there. So a big picture, if you can go straight across the membrane, you're going to. You're not going to use a protein to get across the membrane if you can go straight through that wall. So the only things that go through these proteins are things that are lipid insoluble. That's a fancy word for saying polar or hydrophilic or whatever word you want to say that means you can't sneak through the membrane. Because if you can sneak through the membrane, you're not going to wait for a protein. You're just going to go straight through. Proteins are reserved for all those things we put on our list before. The things that were polar, things that were charged, things that were large, things that were hydrophilic. This is the kind of stuff that's going to go through proteins. There are two kinds of proteins that we use to transport things across the membrane. One of them is what we call carrier proteins. Carrier proteins, we can see that on the left. One of them is what we call channel proteins, like we see on the right. Carrier proteins and channel proteins, the two kinds of proteins I use to get stuff from inside to outside or outside to inside if it matches this description. I like it. Vanessa mentioned, think about proteins kind of like toll roads. That's awesome. Yeah, so if you can just go straight on the regular highway and it doesn't cost you any money, you're good. If you need to take your special toll road to get somewhere because you can't take the regular highway, that's what these protein channels are. Absolutely. They're a little bit more picky, if you will. The two types of proteins we use, carrier proteins and channel proteins. Let's do a little bit of compare and contrast when we talk about these two kinds of proteins. When I talk about a carrier protein, the first thing that you should know about a carrier protein is that it attaches to what it transports. Carrier proteins attach to what they transport. So you can see it in our picture here. We're looking at something like glucose right here. Glucose comes in and attaches to this protein. And then, like we're mentioning in the chat, after I attach to it, my protein actually changes its shape to move that thing across the membrane. So carrier proteins attach to what they're transporting, and they change their shape to get it from one side to the other. So with a carrier protein, carrier proteins are only open to one side of the membrane at a time. They're either open to the outside or they're open to the inside. They're not all the way open to both sides of the membrane. They're attaching to what they transport, and then they're changing their shape so that they open up on the other side to move it. That's a carrier protein. When I talk about channel proteins do not attach to what they transport. They do not attach to it. So channel proteins have this channel, like their name suggests. This is a place that's always open for stuff to move through. When stuff moves through, it's going from the outside, where we're open, to the inside, where we're open. So a channel protein is open on both sides of the membrane, both sides of the membrane. Now, we're going to talk about different kinds of channels, because sometimes a channel can have a block or can have a gate on top of it that makes it so that it's not open. But the gate opens up to allow things to pass straight through. There's no attaching of what we're moving from one side to the other. That never attaches to a channel protein. It's just a channel. It's just a passageway for things to go through. Now, when we talk about carrier proteins and when we talk about channel proteins, these things don't transport stuff at exactly the same rate. What do you think? A channel protein or a carrier protein? Who might transport things faster? Would a carrier protein or a channel protein go faster? Yeah, lots of us voting channel proteins to transport things more quickly. That is correct. If you don't have to change the shape of the way that things go through, you can just go straight through. That's going to be faster. Channel proteins go faster. When we talk about these carrier proteins, I like it, our toll booth analogy coming back here. You got to stop and pay your toll, right? This molecule's got to attach to that protein, and then we've got to change our shape. So a carrier protein is going to take a little bit longer to transport things. Because remember, a carrier protein has to change its shape. Channel protein, as long as there's not a gate blocking it, things are going to go straight through from inside to outside. So channel proteins tend to go faster than carrier proteins. But what I will say about carrier proteins is your cells are pretty legit. They still make these things go pretty fast too. But if you want to do something super fast, super speed, we're going to do a channel protein to do that. So here's a wink, wink, nudge, nudge study tip. I totally recommend you making a compare and contrast table, comparing a channel protein to a carrier protein. How are they the same? How are they different? This is my study tip for you. Make yourself a table. How are they the same? How are they different? When we talk about channel proteins, they're not necessarily always open all the time. The ones that are always open all the time are what we call leakage channels. Leakage channels. Over here on the left, I'm looking at a leakage channel. Remember that channel proteins never attach to what they're transporting. So stuff always goes from the outside to the inside, always straight through. We don't attach. When we talk about a leakage channel, this is the kind of channel that is always open. Leakage channels are always open. But I like their name because it sounds a lot like if you have a leaky sink. If your sink leaks, it's constantly going drip, drip, drip. It's going slowly. Leakage channels, they may be always open, but they're always moving things slowly. So moving things slowly all the time, that's the job of a leakage channel. My other types of channels that I see over here, all three of these fall into the category of what we call a gated channel. A gated channel. I'm going to ask you this question like almost literally every week. So here comes the answer to the question I'm going to ask you repeatedly. When we talk about gated channels, our gated channels are or are not always open. What do we think? Gated channels are or are not? Yeah, exactly. Gated channels are not always open. Look at that. We already know the answer to the question. I'll make sure to ask it like 5 more times today, then we'll be set. We're golden. Gated channel proteins. They have a gate. Something is necessary to open them. Now, once I open them, we see our channel. Our channel is available once they're opened. But I use different kinds of keys to open these gates. So let's start with my channel here in the upper middle. This is called a chemically gated channel. A chemically gated channel. Hey, not a trick question. If I'm a chemically gated channel, what opens me? If I'm a chemically gated channel. Yeah, exactly. I promise this concept is not as hard as you might be afraid. A chemically gated channel opens up with chemicals. In just a bit, we're going to talk about how one of the major chemicals that we use to open these channels, especially in neurons, are called neurotransmitters. Neurotransmitters, a kind of chemical. In this picture, we're seeing a neurotransmitter, but we could use some other chemical to open it. It could be an ion. Maybe it's a bunch of calcium that opens up this channel, or maybe it's glucose or a protein. Whatever it may be, there's a receptor or there's a spot for that chemical key. When that key comes in and opens up this chemically gated channel, now I've got a space for stuff to rush in or out. Remember, channel proteins, as long as the gate is open, stuff can rush in and out. Chemically gated channels open with a chemical. Hey, this one right here is what I call a voltage gated channel. Voltage gated channel. When we talk about a voltage gated channel, how do I open or close these ones? How do voltage gated channels open or close? Yeah, Cal is absolutely right. Voltage gated, I want you to be thinking charge. Voltage gated, we change the voltage or we change the charge. So in this particular picture, I'm looking at this channel closed. Notice that the inside of the membrane has a negative charge and the outside has a positive charge. When things happen in my cell that make the inside of the membrane go positive, suddenly this protein opens up. See how I've got a channel now for stuff to rush in and out? Because the inside is positive when it used to be negative. So if we flip the inside from negative to positive, that could open or close these channels. If we go from positive to negative, anytime we talk about voltage gated channels, you should always be thinking charge. Voltage means charge. One last kind of channels for us to mention, that's these ones here. These ones are what we call mechanically gated channels. When we talk about a mechanically gated channel, we're going to use a physics word, and that's mechanical energy. But let's put it in easier words. Help me out in the chat. How would you describe how a mechanically gated channel is opened? Yeah, so something like pressure, vibration, force. Hey, I'm going to put it as simple as possible. I'm going to say that we have to push it. Mechanically gated channels, we have to push on these channels, whether we push on them because of a sound wave, whether we push on them because you're touching something, so there's pressure or force. A mechanically gated channel gets pushed open, or it gets forced open because something literally changes the shape of that gate. Big picture, your body has carrier proteins and channel proteins. Carrier proteins open on one side, then open on the other side. They attach to what they move. Channel proteins never attach to what they move. There are different kinds, though, of those channels. We've got those leakage channels that are always open. They move stuff really slowly, dripping faucet. Then we've got these gated channels here. When you open up a gated channel, think about that like turning on a fire hose. Stuff is going to go really fast when you turn on that hose, when you open that gate. Maybe we use a chemical to open that gate. Maybe we use a charge to open that gate. Maybe we push things open. Whenever I open these gated channels, stuff moves fast. How do we feel about our types of channels and carrier proteins? How do we feel right now? Or what questions do we have? I'll also open the floor to questions. I talked a lot. To Audrey's question about whether this is something that both carriers and channels had. So carrier proteins are kind of their own beast. There's only one type. They're just called carrier proteins. Channel proteins are the ones that have all of these different things. So a chemically gated channel or a voltage gated channel, mechanically gated channels. So it's all, this is stuff that's just for those channel proteins in particular, since they all have a passageway for stuff to go straight through. All right, so let's talk about, I'm gonna let, for those of you who haven't had a chance yet, I'm gonna let you learn about the cute dogs by yourself, because it's a fun analogy for us to talk about our types of channels, gated channels. What I wanna do though, is I wanna hone in on this terminology. When I use a channel protein, here's something I want you to write down for me. Whenever I use a channel protein, I am doing facilitated diffusion. So whenever you use a channel protein, you're doing facilitated diffusion. Facilitated diffusion is just like regular diffusion, except we're using a protein facilitator to do it. In other words, we're doing diffusion with the stuff that can't diffuse straight across the membrane, the stuff that I need a special toll road for. Facilitated diffusion, just like normal diffusion, but with protein, like several of us have mentioned in the chat, because we're doing a form of diffusion, we're always going to be transporting stuff from high to low. Facilitated diffusion, like regular diffusion, we always go from high to low, which means that stuff's only ever go from where there's a lot of it to where there's a little of it. Hey, when we go from high to low, from a lot to a little, does that take energy? Going from a lot to a little? Yeah, no energy required. No energy required. When we go from high concentration to low concentration, that doesn't take any energy. So here's an important idea I want to make sure you guys catch. Anytime I use a channel protein, so whether it's a voltage gated channel or chemically gated channel, I don't need energy to open or close those channels. Even if they have a gate, it doesn't take me energy to move stuff through those channels, because they're only ever going to go from high to low. We're always transporting stuff from high concentration to low concentration. Hey, guess what? Here's where we get to draw Dr. Allis's favorite thing from unit number 1, the thing that never goes away. Look at our salty banana cell, back to haunt us again, as always. Yep, a food, right? My favorite thing is food, let's be real. All right, we're talking about our salty banana cell, which means I have a lot of what on the inside? What do I have a high concentration of inside my salty banana? What's inside there? Yep, potassium, K+. Lots of potassium inside my cell, lots inside. What do I have a high concentration of outside? What's outside that cell? A whole lot of 2 things there on the outside. My salty stuff, right? Sodium, first part of salt, and like several of us mentioned, chloride. Got a whole lot of sodium and chloride outside my cell. I've got a whole lot of potassium inside my cell. Hey, so check this out. Let's say I make a channel protein whose job in life is to do facilitated diffusion for potassium. So here, I'm going to draw myself a little channel here. Here's my little channel protein for potassium. This channel protein here is going to help me do facilitated diffusion. You all told me if I do facilitated diffusion, I take things from where there's a lot to where there's a little. So if I've got a channel protein for potassium, is it going to bring potassium into the cell or take potassium out of the cell? Which way is it going to move potassium since we're doing facilitated diffusion? Yeah, exactly. Potassium is going to go out. Facilitated diffusion, we always go from where there's a high concentration to where there's a low concentration. When I use a channel protein to transport potassium, it is always leaving. It's always leaving my cell. Okay, let's do a channel protein for sodium. Let me draw myself a sodium channel over here. When I open up a channel protein for sodium, which way is sodium going to go? Is it going in or going out in facilitated diffusion? Yeah, sodium is going in because I've got a lot of it outside and not as much of it inside. Let me try to move that a little bit. A lot of it outside, not as much inside. Sodium's going to go inside. What about chloride? Where's chloride going? My last one here. Where does chloride go in our carrier, or our channel protein, excuse me? Yep, chloride is also going in. Hey, this is a must-know concept right here. We need to know our salty banana cell, that there's a lot of potassium inside our cells, a lot of chloride on the outside. That's important because when I start doing channel proteins can only move stuff from where there's a lot to where there's a little. I can only ever move potassium to the outside with a channel protein. I can only ever move chloride and sodium to the inside with a channel protein. These channel proteins only do high to low. So never tell me on homework or on the exam that we're going low to high. Never tell me we're going the wrong direction with a channel protein, because channel proteins only go from high to low. Now, I'm going to mix it up on us a little bit, and I'm going to take us all the way to neurons. So let me show you the page we're going to go to here. We're going to go right here. Can you help me out in the chat? What page in lesson number 4 is this? I may be seeing page 8. Does that sound right when we start talking about neurons? Okay, page 8 to 9. So obviously we're at the very end of the packet. We'll go back to our active transport, but I want to make sure I hit this because it ties in well to what we just talked about. When we talk about the way that neurons work, let me give you some terminology here. Neurons are what we call an excitable cell. An excitable cell. What that means is the way that they work, or the way they get stuff done, is they change their membrane charge. They change their membrane charge to get stuff done. When a neuron isn't doing anything in particular, when it's not hearing a message from its neighbor, when it's not talking to somebody, a neuron is chilling out at what it's called resting membrane potential. Resting membrane potential. Resting membrane potential, the easy way you can think about this is it's the normal charge. It's the normal charge. It's kind of like how you and I, we have a normal temperature of 98.6. The normal charge on the membrane is its resting membrane potential. Yeah, and Elapine is totally right. The resting membrane potential, the normal charge on a neuron, is -70 millivolts. What that means is inside is 70 millivolts more negative than the outside. The outside looks 70 more positive. I don't make you learn a lot of numbers in this class. Numbers aren't my favorite either, but we do need to know this number. Make sure to underline, highlight, star for yourself, negative 70 millivolts. This we call resting membrane potential for a neuron. When a neuron is waiting to hear a message from its neighbor, when it's just doing its normal life thing, inside is much more negative than outside is. When a neuron hears a message and decides that it should go talk to its neighbor, what it's going to do is change its membrane potential. So we're going to go from resting membrane potential at negative 70 all the way up to positive 30. We're going to change completely from negative to positive, and that's going to allow us to talk to our neighbor. This is going to be my favorite graph of unit number 3, and I know you're going to see it on the homework this week. I can't remember if it's on the exam, but you should assume that it is. I just don't remember. Okay, so this graph is on page 9. We've got to understand this graph. So I want to take up a bunch of time for us here. When you look at this graph, this is a graph of membrane potential. That's what my x-axis labeled here, membrane potential. I want you, next to this thing that says membrane potential, I want you to write underneath it, membrane charge. Membrane charge, because that word potential is weird. It just means the same thing as charge. This is a graph that shows me the charge of the plasma membrane of a neuron. From the beginning, where it's at rest, where it's listening to its neighbors, to when it completely freaks out, to when it talks to its neighbors. This is what a neuron gets to talk to its neighbors, to when it goes back to being normal, to wait for another message. This graph shows me what's going on inside versus outside on a neuron, from beginning to end, when it receives a message to when it gets back to normal, back to rest. Let's talk about this graph. Remember that we said that one of the numbers we need to know is negative 70. Negative 70 is my resting membrane potential. This is the charge on the inside compared to the outside. So when a neuron is at rest, resting membrane potential, it's at negative 70 millivolts. Now say that neuron is next to a friend, and that friend decides to send it a message. This part of the graph here where it says stimulus applied, I think you should change that stimulus word to message. Message. What's happening when a neuron's at rest and it gets a message is that message opens up some of those chemically gated channels that we just talked about a little bit ago. The message is a kind of chemical called a neurotransmitter. A neurotransmitter. Basically, it's the kind of text message that neurons use with each other. So if I'm chilling out at rest and all of a sudden my neighbor texts me, they send me a neurotransmitter. Depending on what that text says, that might open up some channels that move ions to make the inside of my cell get more positive. So remember those channels we were looking at? They can move things into the cell or move things out of the cell. The specific kind of channel that we're seeing open right here on my graph is a chemically gated sodium channel. Chemically gated sodium channel. Let's see if we can remember. Actually, let's help ourselves out before I just make you recall it. Guess what we're drawing? My favorite. All right, let's start on the outside this time. Who lives on the outside? of my salty banana cell up there. Who's outside the cell? I know you all hate this salty banana by now. I promise you it's never going away. It'll be here all semester. Yep, we got that sodium, we got that chloride. Okay, here's the outside, and the inside again, since it's a banana, it's gonna have a whole lot of potassium, absolutely. Sodium and chloride on the outside of the cell, potassium on the inside. Friendly reminder that we are transporting things from where there's a lot to where there's a little. So sodium is coming in, chloride is coming in, potassium is going out. Remember, we talked about this just a minute ago. Because we always transport from high to low, here's the way stuff moves. So check this out. Here I am down here getting the text message from my neighboring neuron. That text message attaches to a chemically gated sodium channel. I'm opening up a chemically gated sodium channel. Which way does sodium move when I open a channel protein for it? Where's sodium going when I open up its channel? Yeah, exactly. Here it is right here. When I open up a channel protein for sodium, sodium comes inside. Hey, look, sodium has a positive charge. If something has a positive charge, I have a special name for that kind of ion. What's the special name for an ion with a positive charge? Does anyone remember what those ones are called? Exactly. Those are called cations. Sodium is a cation, has a positive charge. When I open up a chemically gated channel for sodium, in comes sodium with its positive charge. And check out what happens to my membrane charge. I go from -70, I start to get less and less negative. I start to get more positive because I'm bringing in a cation. I'm bringing in something with a positive charge. The way I got this sodium inside is I got the right chemical that attached to my chemically gated sodium channel and started to bring sodium inside. Now, if that chemical brings in enough sodium, we hit an important value, another number that we need to know. The next number we need to know is something called threshold, -55. -55, so that's another number for us to know. When the charge on a neuron's plasma membrane gets all the way up to -55, from its normal is down here at -70. When I bring in enough sodium to get to -55, my neuron's membrane says, whoa, we are serious about this message. This is some hot gossip that I've got to share. So we hit -55, and at this point, my membrane charge is too wrong. My charge has freaked out. Which kind of gated channels open when the charge changes again? What kind of gate has to do with charge? Yeah, exactly. That's those voltage gated. Voltage gated. When I hit threshold, voltage gated sodium channels open up. Voltage gated sodium channels. These ones need the membrane charge to be different, right? That's what voltage gated means. The charge has to be different. When we're down here at -70, these ones are like, I'm closed. It's -70. If we can bring in enough positive charge to get the membrane up to -55, my kinds of gates that open with charges, my voltage gated sodium channels, they'll open up. Hey, it's still a sodium channel, Which way is sodium moving again? Does sodium go in or out with those channel proteins? Yeah, sodium's coming in, right? And sodium still has a positive charge. Sodium's still a cation. When I open up these voltage-gated sodium channels, this neuron is committed. Like, we're going for it. All the sodium rushes inside this cell, rushes, till the point that the inside membrane of my neuron gets all the way up to the last number we got to know. That's positive 30. All the way up to positive 30. When we are all the way up to positive 30, our membrane charge is completely wrong. But the good news is, when I get my membrane charge completely wrong, there's a type of channel up here that's going to help me to send a message to my neighbor. It's going to help me to text my neighbor with the hot gossip. The kind of channel that's going to, one of the kinds of channels that opens at positive 30 is a voltage-gated calcium channel. I don't think I made you guys know this one now. This is a bonus one for you for future reference. The kind of channel that's going to help me talk to my neighbors is what I call a voltage-gated calcium channel. This one helps me release neurotransmitters. Neurotransmitters. For any of my friends that work through the lessons, did I mention this one in the guided lesson or not yet? I may not have even talked about it. No? Okay. So just as a heads up for you, this is coming soon. Well, in Unit 3, we'll talk specifically about how I release neurotransmitters. It's because of voltage-gated calcium channels. Voltage-gated calcium channels. So this is its own deal over here, the way that this neuron talks to its neighbor. But let's focus on the neuron itself. The neuron itself, it's sent its message to its neighbor. It's thrilled with itself. Woohoo, I sent that text. But then it kind of has a moment of clarity and says, oh snap, my charge is positive 30 and I'm supposed to be negative 70. This is bad news. I am way the wrong charge. Up here at positive 30, to help our neuron fix itself, to get its membrane charge back to normal, this is where I'm going to see voltage-gated potassium channels. Voltage-gated potassium channels. Now, remind me again, voltage-gated, what does that mean if a channel is voltage-gated? How do I open those? Yeah, so Kaylin's right. I probably should have asked that question, right? Gated means we're not always open. Yeah, and the way that I get us open is with changes in my charge, with voltage problems. So at positive 30, up here at the top, when I'm completely the wrong charge, I'm supposed to be negative 70, somehow I got out of control, I'm at positive 30, it's time to go back. A voltage-gated potassium channel moves potassium. When I open up a channel protein for potassium, is potassium going to go in or out? Which way does potassium move? In or out? Yeah, check out my little cell over here, my salty banana cell. Potassium is going to go out because there's a lot of it inside, not as much outside. But hey, check this out. Potassium has a positive charge. When these positive charges leave the cell, it actually makes the cell more negative. See how the charge on the inside keeps getting more and more and more negative? That's because I'm taking these positive potassiums and I'm spitting them out. I'm doing subtraction, basically. So I go from being all the way up at positive 30, I go back down, 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 down to resting membrane potential. And then I actually go a little bit too negative as we can see down here. That's because these voltage-gated potassium channels, they don't close fast enough, so we actually spit out too much potassium. We get a little bit extra negative down here. But the good news is I can use a couple of different mechanisms to get back to where I'm supposed to be. One of the things that helps me to get back to where I'm supposed to be is that kind of channel protein that was always open. Which kind of channel protein is always open? What were those ones called that were always open? Yeah, those ones were called the leakage channels. The leakage channels. Oops. Leakage channels are always open. Remember, they move things slowly. So I slowly get some of my charge back to normal using leakage channels. The other way I get it back to normal is something we're going to talk about here in just a moment, something called the sodium-potassium pump. The sodium-potassium pump. Hey, before we even talk about this, not a trick question, I promise. What do you think the sodium-potassium pump moves? Not a trick question. What is the sodium-potassium pump gonna move? Yeah, exactly. It's gonna move sodium and potassium. So, two ways that I get from being too negative back to normal. I can use those leakage channels to kind of leak me back to normal a little bit. And I can use my sodium-potassium pump. And Elapine is totally right. This is actually going to be our first example of active transport, where I have to use some energy to do that. So this is no longer passive transport when I'm doing this. The leakage channels are, but I'm going to have to bring out the big guns. Going to have to use some energy to get us back to normal. I want to pause because I know that this is a big, important concept. I want to give you a moment. If you can put to words any questions that you have, can you put them in the chat for me? Or you can shoot me an emoji. Okay, so Elapine is mentioning some terminology that would be good for us to know. The terminology that she's mentioning is depolarizing and repolarizing. So over here on the left side of my graph, when my charge gets more positive, that's a process that we call depolarization. Depolarization. So here, let's actually put, I'll put that. Let's try again. Depolarization. That's a fancy word for saying membrane charge gets positive. Depolarization. Membrane charge gets positive. See, when a cell is at rest, when it's at resting membrane potential, the word that I use to describe it is I say that it's polarized. It's polarized. That is a word from lesson number 2. We talked about that a long time ago. Does anyone remember what it meant when we said that a cell is polarized? All of your cells are. Polarized is a good thing. Yeah, there we go. So Fanshin's correct. Polarized means that our membrane has a charge. A polarized cell has a different charge inside versus outside. Polarized cell, different charge inside versus outside. When a cell is at rest, it has a charge of -70. Our cells, when they're polarized with their different charge inside and outside, it's -70. When I get more positive, so even when I just start getting more positive, just a little bit more positive, we call that depolarization, making my membrane charge more positive. So depolarization is what we see on the left side of the graph here, making my charge more positive. Because remember, when it's polarized like normal, it should be down here at -70. When you make me more positive, we're going away from normal. We're depolarizing. When we get completely depolarized, so we're completely the wrong charge up here, that's when we start the process of repolarization. Repolarization. And when we do repolarization, we're trying to get back to normal. We're trying to go back to -70. So repolarization is when the membrane charge gets negative, when the membrane charge goes down. So we're repolarizing on this side of the graph, trying to get back to normal. Now I actually have a word that applies to this little part of my graph. This part of my graph, we are too negative, or we're extra negative. Does anyone happen to know what we call it when we're extra negative? What happened to this cell down here? Will help us out. So it's a beginning, a prefix, just like we used with our tonic words. What prefix do you think I'd put if something is extra polarized? Yeah, Fanshan's right. Hyperpolarized. Hyperpolarized. When my cell gets a little bit too negative, I call that hyperpolarized. So we depolarize when we get more positive. We repolarize when we get too negative, or when we get more negative, excuse me. If I get too negative, I call that hyperpolarized. A regular polarized cell, though, is at this -70. It's at normal, at rest. Great question. Thank you for that question. Give me your honest emojis. How do we feel about this graph right now? Christian's wondering if it'd be easier to see upside down, right? Yeah, so we're kind of across the board. That's okay. What I'm going to recommend for you, reread the guided lesson. I'm going to post this video, rewatch our discussion here of this graph. And if we want to, we can try to chat this up again tomorrow too, during our exam review. This is not something that automatically makes sense, for the record. This is something every semester my students say in Unit 1 that it's just terrible. But by the time we hit it again in Unit number 3, trust me, you're going to understand it way better. So put in the work now. We're going to work on it, and we'll see how we can get to with it. All right, I have just a little bit of time left today. What I want to talk with you about during our time that we have left today is the two kinds of active transport. One of them we mentioned right here, the sodium-potassium pump. We're also going to try to squeeze in a discussion of the sodium-glucose cotransporter. So everything we've talked about, the way that a neuron works, all these different types of gated channels we talked about, all of this stuff has been passive transport. Remind me in the chat, passive transport, do things go from low to high or high to low when I do passive transport? Exactly. Things are going from high to low, no energy required. We're going to transition into talking about active transport. Active transport is how I move stuff from low concentration to high concentration. Yeah, Audrey put a question in the chat asking about passive transport. Correct. It is always from high to low, every single time. So anything I tell you that is an example of passive transport, we are always going from where there's a lot of something to where there's a little something. Absolutely. Okay, so let's switch. Let's switch to going from where there's a little bit of something to where there's more of it. To help us with this discussion, we're going to do two examples. First example is what we call the sodium-potassium pump. That thing that I mentioned previously on the slide, the sodium-potassium pump. So let's chat about this pump before we talk specifically about the kind of active transport it is. When I talk about the sodium-potassium pump, first thing we need to know is which direction things are moving. And I promise these aren't trick questions. Let's look at our picture here. I can see some sodium right here. Here's my little arrow for it. Based on my arrow, is sodium moving in or out of the cell? Can we tell? In the sodium-potassium pump, sodium is moving out. Sodium moves out. When I look at my picture here, here's my potassium with an arrow that's pointing in. Potassium is going to move in, moves in. Guess what? I get to do my favorite again. We get to draw another salty banana cell. Back to haunt us once again. All right, where do I have a lot of sodium? Is there a lot of sodium inside or outside? Where is there a lot of sodium? Yeah, there's a whole lot. Remember, it's a salty banana. There's a whole lot of sodium on the outside. Where do I have a whole lot of potassium? Where's there a lot of potassium? K. Inside or outside? Yep, K's on the inside. Okay. Here is where I have a lot of these things. A lot of sodium on the outside, a lot of potassium on the inside. Now, here's our sodium-potassium pump. What the sodium-potassium pump does is it moves sodium to the outside of the cell. Sodium's going like that. It's moving potassium into the cell. I already have a lot of sodium out here. You told me that I already have a bunch of sodium on the outside. I already have a lot of potassium on the inside. And yet, the way that this protein moves things is sodium goes from low to high, and potassium goes from low to high. I am moving two molecules, the terminology we use is up their concentration gradient. Up the concentration gradient. Think about concentrations like a hill. So at one end of the hill, I've got low concentration. At one end of the hill, I've got high concentration. When I take sodium and I move it outside of the cell, there's already a lot of sodium on the outside. There's not very much on the inside, but I'm still taking that sodium and I'm pushing it up the hill. When I go up the concentration gradient, that takes energy. With potassium, I've already got a lot on the inside, but I'm taking the little bit on the outside and I'm pushing it inside. I'm going up the hill. That takes energy. So our question down here about why do these movements take energy? Both of these things are moving up their concentration gradient. Both of these are going uphill. That requires energy. When anything moves uphill, that requires energy. Now, for this particular type of transport, the sodium-potassium pump, we're doing something that's called primary active transport. Primary active transport. Anytime you see active transport, it takes energy. When we talk about primary active transport, where does that energy come from? What's the energy for primary active transport? Does anyone know? Yeah, so my energy is ATP. Remember how we talked about ATP is my energy money in the cell? I use a molecule of ATP. I steal the energy out of it to move potassium or to move sodium out of the cell, to move potassium into the cell. In primary active transport, here's another note for us to make about it. In primary active transport, two molecules go up their concentration gradient. Two things are going uphill. In the case of the sodium-potassium pump, sodium goes uphill by leaving the cell. And again, in the sodium-potassium pump, potassium goes uphill by coming inside. Because both of these things are going from low to high, the only way I can make that work is by using ATP, by using stored energy. One of the things that you need to know about the sodium-potassium pump is its job, why the cell does this. The simplest way to talk about why the cell does the sodium-potassium pump is this is what polarizes the membrane. This is what polarizes the membrane. Now remember, we just talked about this a little bit ago. A polarized membrane has a different charge inside compared to outside. And that's a good thing, because we just saw with our neuron graph, we need to be able to change the membrane charge in a specific way, the way that we want to. For us to be able to do that, we got to be polarized first. So the sodium-potassium pump polarizes the membrane. That's the job of this one. The other active transport that we need to know is we need to know the sodium-glucose cotransporter. The sodium-glucose cotransporter. Just like last time, let's answer our questions here. When you look at our picture, which direction does it look like sodium's going? Is sodium going inside or outside? Which way is sodium going? Exactly. Sodium's moving in, right? Hey, glucose is shown here in green, those little green hexagons. Which way is glucose moving? Yeah, glucose is also moving inside. Absolutely. Glucose is also moving inside. You know what time it is. We get to draw Dr. Hollis's favorite. Where do we want to start? Inside or outside? I'll let you pick. I always pick. I'll let you pick. In or out? All right, we got to vote for inside. Okay, what's on the inside of our cell? Yeah, so we got the thing we've always been talking about, right, is potassium. We need to identify where I have sodium. Where's there a lot of sodium? Again, is that inside or outside? Yep, sodium's on the outside. And hey, while we're at it, because we're talking about moving it, where do I find a lot of glucose? Inside or outside? Where's the glucose? Yeah, glucose is also inside. That's another one of those. Remember, bananas have a lot of sugar, so that's another one for us to remember. There's a lot of glucose on the inside, along with that potassium, along with those proteins, friendly reminder. On the outside is where I've got that sodium and the chloride. Okay, so check this out. In the sodium glucose cotransporter, which way, we said the sodium's moving in, right? When sodium moves inside, is that going from high to low or from low to high? when sodium moves inside, is that going uphill or downhill? Make our little hill again. Yeah, when sodium moves inside the cell, sodium is going down its concentration gradient. Down, it's going from high concentration to low concentration. Glucose is also going inside. Is glucose going from high to low or low to high? Which way is glucose going? Yeah, a couple of us are chiming in here. Glucose is going up its concentration gradient. Glucose is going up because I've got a whole bunch of it inside. I already have a lot inside. I don't have as much outside. So I'm going from low to high. I need energy to get glucose into the cell because glucose is going uphill. Glucose is going from where there's not a lot to where there's already a bunch. That's going to take energy. The energy to pull glucose inside comes from right here. It comes from the fact that sodium is going down its concentration gradient. When sodium goes from high to low, that releases some energy. It was high up here, it's low down here. Think about a rock rolling down a hill. No energy required. And when that rock gets to the bottom of the hill, it's still rolling. It's still got some energy. The way that we do secondary active transport is somebody needs energy. In this case, glucose needs energy. The energy that it's getting is the fact that sodium is moving down its concentration gradient. Sodium is releasing energy while it moves. That energy is snatched or it's stolen by glucose. So the energy in secondary active transport in this example is coming from the movement of sodium. In secondary active transport, so to our top question, how does it work? One molecule moves up its concentration gradient using the energy of the one that moved down. Some of the words from your guided lesson, things like piggybacking, things like hitchhiking. We're, just like Kaylin mentioned, we are not using ATP when we do secondary active transport. So that'd be a good note to put. No ATP is used for secondary active transport. We're not using our energy money to do this. But we are using the energy of somebody going from high concentration to low concentration. So consider this for our cell. Our cell just used ATP to do that sodium potassium pump, to pump all of this sodium to the outside of the cell. It used ATP to do that. And then we go right next door and we let all that sodium just sneak back inside the cell. Why does it make sense for a cell to do the sodium glucose cotransporter? Why is it willing to, I'm going to put in air quotes here, waste the movement of sodium back into the cell? Yeah, Elapina's right. It has to do with this right here. It has to do with the fact that the cell so badly wants glucose. And why does the cell want glucose? What's the job of glucose in a cell? Kaylin is being all too true. She's like, glucose is addictive. No joke. As I sit here drinking my sugar coffee, right? Yeah, glucose, the way I like to think about glucose is a cell's favorite food. It's a cell's favorite food. It's the easiest for the cell to break down into ATP. This is the fastest way for a cell to make energy. Hey, have we talked about this? There's one kind of cell in your body that can only make energy from glucose. Have we talked about who that is? Does anybody know? Yeah, Kelly's right. The only kind of food that your neurons can eat is glucose. It's so important to have a blood sugar that's within normal range because of those neurons. They need that glucose. It's the only kind of food they can eat. So your body actually has ways of turning other energy sources into glucose to make sure that your neurons have enough glucose to survive. All right, let's think big picture here. We talked about secondary active transport, where somebody moves down their concentration gradient to allow somebody to go up. We also talked about primary active transport, where we use ATP to move two things up. Earlier in the chat, when we first started talking about active transport, somebody summarized for me what the biggest idea here with active transport for us to know. Here's an underline highlight star idea about active transport, primary active or secondary active transport. Here's an important idea. If a cell uses energy to do something, it must be important. If a cell uses energy to do something, it must be important. That's an underline highlight star idea. Your cell is willing to burn its energy monies to move sodium outside and to move potassium inside, because it's really important that your cell be polarized. It's willing to spend energy monies to polarize the membrane. It's also willing to mess up that hard work of pushing all the sodium outside. It's willing to mess that up, use that energy to bring in glucose, because glucose is its favorite food. If a cell uses energy to do something, it must be important. So make sure as you're reviewing these two types of active transport, we can explain why these things are important, why a cell needs them. I am out of time. I want to pause for a moment to ask if we have any questions right now that we can think of. And if we don't have questions, shoot me an emoji. I'll send you my penguin. How do we feel about lesson number 4 now? Do we feel any better about lesson 4? I am trying to draw a small penguin, and this is just terrible. He probably looks about how we all feel, right? Yeah, Kaylin wants to know if we are in fact still alive. My penguin would tend to suggest otherwise. He's looking pretty bad today. Again, he's looking about how we're all feeling, right? Yeah, Audrey says she'll never look at bananas the same way. Yeah. I'm telling you, at the end of the semester, we'll have to pull out some salty bananas together. We can do the salty banana challenge. That was kind of fun. All right, well, I am probably going to end the recording, but here's the reminder that tomorrow we're going to have an exam number 1 review session. So tomorrow at 1 o'clock, please plan to stop by if you've got time. I am going to leave that completely up to you all, what we would like to discuss. So I will open the floor here in the chat now and my email inbox. If you have particular things that you know you'd like to talk about tomorrow, if you can let me know, I can work on preparing the slides that we need for it. But again, that's tomorrow at 1 o'clock, and we will have one last review session Monday at 1 o'clock. Again, that's driven by you all. So let me know what you want to talk about, and we'll make sure we discuss that. So good luck to our friends on the recording. Hope to see you all tomorrow.